Okay, so let's take a look at VSEPR structures. Now, VSEPR structures are basically the three-dimensional structures of molecular compounds. Okay, so molecular compounds are basically covalent compounds, right? And because of the electron sharing between different constituent atom species, what's going to happen here is there's actually going to be some kind of electronic repulsion. So this electronic repulsion, the repulsion between electrons, causes unique shapes and bond angles to be created, right? So this is essentially the three-dimensional structure of the compounds that we're going to be looking at, right? Now, VSEPR actually stands for valence, shell, electron, pair, repulsion. And this is a theory that basically will help us to predict some of the structures of these compounds, right? So we're going to be using this theory, and this theory is going to be based on the amount of bonding atoms and central atoms as well as the electrons that are found around the bonding atoms. All right, so we'll take a look at all of this stuff. So when we're looking at any kind of compound, when we're looking at any kind of molecule specifically, right, we need to first kind of characterize the central atom as well as some of the bonding atoms. Now, some of the rules for central atoms, if we're looking at central atoms, some of the rules for central atoms is that it's going to tend to be the most electropositive or the least electronegative atom. Now, the only exception here is hydrogen. Hydrogen is just too small to be a central atom, right? So the exception here is hydrogen. When hydrogen's present as a constituent atom, it's never going to be the central atom, right? Okay, so, and for the most part, it's going to always, it will usually be carbon, right? Or any kind of tetravalent atom. And what a tetravalent atom is, it's any kind of atom that can form up to 4 bonds to form a stable octet, right? So for most of this case, the central atoms will tend to be the least electronegative or will be carbon for the most part. Okay, so now that we understand what a central atom is, right? When we're looking at VSEPR structure, when we're looking at covalent compounds, referring back to the molecular orbital theory and the valence bond theory of how covalent bonds are formed, right? The reason that these atoms will partake in a covalent bond is because of the fact that they want to form a stable octet, right? They want a filled valence shell. So the bonding atoms are going to be around the central atom, right? And the electrons surrounding the central atom are going to be called electron groups. Okay, so the electron groups is basically all the electrons that surround the central atom, right? And there's going to be 2 sets of electron groups. Right? The total number of electron groups are going to be basically encompassing non-bonding electrons as well as bonding electrons. Okay, so we're going to have a set of non-bonding electrons and bonding electrons. So I'm going to show you guys this by demonstrating this using the Lewis dot structure. Right? Like for instance, if we're looking at methane, right? And when we looked at designing Lewis dot structures, we also used the formula where the total number of bonds is equal to total number of electrons in the stable octet minus the total number of electrons in the valence shell, right? So the number of valence electrons divided by 2. And this formula is actually pretty useful in designing these structures, right? So if I looked at the methane here, CH4, right? Methane is going to have carbon being a central atom, right? I'm going to do carbon's electrons in orange, and it's going to donate one of each electron, and as a result, hydrogen, I'm just going to do this in red, is going to receive that electron and donate its own electron, right? So this is like a normal covalent bond, right? And you can see that all these guys have a stable octet, right? So you can see that the hydrogens are happy, they have a stable octet, they have access to all these electrons, and the carbon is happy and it has access to all these electrons. Okay, so now you can understand that, yeah, this is going to be a covalent compound. Now, what we want to understand here is that the total number of electron groups that is surrounding the central atom, which is going to depend on your VSEPR structure, is going to be 8. Now, what we can look at here is each of these electron groups are purely bonding electron groups, right? So there's one bonding electron group here, one bonding electron group here, one bonding electron group here, and one bonding electron group here. There's 4 pairs of bonding electrons. Okay, so there's 4 pairs of bonding electrons, 4 pairs of bonding electrons, and there is no set, or there's no pair of non-bonding electrons, right? So what we call non-bonding electron pairs are called lone pairs. So lone pairs are non-bonding electron pairs. All right, so we're going to basically be looking at a combination of bonding electron pairs and non-bonding electron pairs when we're looking at the electron groups surrounding a central atom. So having said this, the VSEPR structure is going to be dependent on both of these two things. If we're looking at the electron groups of any kind of species, it's going to tell us the geometry of that compound, right? So let's take a look at another example. Let's say we're looking at water. So if we're looking at H2O, right? So the structure of water here is going to basically be, I'm going to have my central atom. So we already said that hydrogen can never be a central atom because of the fact that it's too small. What we're going to do here is I'm going to put oxygen as my central atom, and it's only going to have to donate 1 electron for the hydrogens to form a stable octet. So the hydrogen here is going to donate 1 of its electrons. Whoops. It's going to donate 1 of its electrons, and it's going to receive 1, right? So we use this notion of equivalent exchange where we donate 1 electron, we receive an electron, and this hydrogen will do the same thing. And as a result, we can see here that there is a stable octet that's being fulfilled for the hydrogens, and there's also going to be a stable octet that is fulfilled for the oxygen. In this case, we can notice here that we have a single set of, we have one set of bonding electron pairs for the oxygen to hydrogen. We also have another bonding electron pair between this oxygen and hydrogen, and then we have these 2 lone pairs that we can see up here. Okay, so we have 2 lone pairs, and I'm going to call BP a bonding pair, bonding electron pair, bonding electron pair, and we can also see that there's 2 bonding electron pairs. And the total number of electron group is actually the sum of the non-bonding electron pairs. We should write pairs here. Let's write that in blue. As well as the bonding electron pairs. Right, so the electron groups, I'm going to call it EG, is basically a sum of the non-bonding electron pairs plus the bonding electron pairs. So the non-bonding electron pairs we'll call it lone pairs, and the bonding electron pairs we'll call it BP, right? So that's basically, we can summarize all of this using this simple equation, right? That EG is equal to LP plus BP. And this electron geometry is what's going to be useful in determining what kind of shape, what kind of 3-dimensional structure we actually have for our compound. Okay, so we stated earlier that if we determine the number of electron groups surrounding a central atom, we could actually make a prediction on the general 3-dimensional structure, the 3-dimensional VSEPR structure of the compound. Now we also stated that electron groups, e.g., I call this electron groups, are basically, or can be defined as the sum of the lone pairs, which are the non-bonding electron pairs, plus the bonding electron pairs. Now the bonding electron pairs can also be analogous to the bonding atoms. So we can call it BP or BA. I think it's easier to actually look at this in terms of bonding atoms. right? And we know that we can actually determine the shape of the compound based on the central atom in this set of electron groups, right? Now, to make it, for simplicity's sake, what we're going to do here is we're going to assume here that the lone pairs surrounding a central atom is 0. There are no non-bonding electron pairs. And the reason we're doing this is because we want to get a general architecture, a general three-dimensional VSEPR architecture of the compound. Okay, we're going to later explore that if we do have the presence of lone pairs, what's going to happen is we're going to have slight deviations in the electron geometry. And this is literally what the electron geometry is. It's a general three-dimensional VSEPR architecture as long as there are no lone pairs. Okay, so this is really what the electron geometry is. Okay, so in that sense, the electron groups will just be equated with the number of bonding electron pairs. Okay, so that's what we're going to do to find the general electron geometry. So let's say that we have two electron pairs. Okay, or we have two electron groups. Okay, so we have two electron groups. The electron geometry is going to take a linear type of geometry, and what this will look like. The central atom, what we're going to do here is we're going to use I'm going to use red to represent the central atom. Okay, so red is my central atom here. Okay, and I guess I can do for the bonding atoms, I'm going to use purple. Okay, so let's do purple for bonding atoms. Okay, and what my structure will actually look like, this is my central, this is my central atom. Okay, so if we have two electron groups, assuming that there are no lone pairs, we're going to have two bonding electron pairs or two bonding atoms. What we're going to essentially have here is a structure that will kind of look like this. Okay, and these are both single bonds, so you can assume that they have the same bond length. And this angle here, which I'm going to show you guys, is 180 degrees between the two bonding atoms. Okay, so the bond angle is 180 degrees. Okay, so that's what the electron geometry linear will look like, right? And the angle is 180 degrees, and this is with two bonding atoms. Okay, now let's say we have three bonding atoms. Okay, so we're going to have three electron groups. So I'm going to just draw that here. We have three electron groups, right? Whoops. Let's just try to keep this consistent a little bit. We have three electron groups. This electron geometry is actually called Trigonal Planar. Okay, planar means in the scope of a plane. We know that a plane is a combination of two dimensions, right? Or two axes. And what trigonal planar will look like is, in general, this is our central atom, right? We're going to have a bonding atom here, here, and here. Okay, now if you guys think about this in terms of a plane, right? If this is our plane, right? So assume that this is our plane here, right? You would essentially see the central atom here, a bonding atom here, here, and here. Okay, so that's going to be in the scope of a plane. So try to visualize this. I think for you to truly understand and truly appreciate these VSEPR structures, these three-dimensional structures, I would really advise you guys to get a molecular kit, so that way you guys can kind of play around and see this. And you can notice here that the angle between the bonding atoms, this angle here is 120 degrees, right? Because we know that if these three bonding atoms are basically in the same angle and same bond length away from the central atom, that the full revolution of this within the plane should be 360 degrees, right? So this is a 120 degree bond angle. Okay, so that's what trigonal planar is. It's three bonding atoms, right? Now let's take a look at the next case. Whoops, let's make this orange. Let's take a look at the next case. And in this case, maybe I should add a little bit more space here. Okay, so in the next case, we're looking at four electron groups. So four electron groups is known as tetrahedral. Okay, and what tetrahedral will look like, here's our central atom. One bond will be in the plane of the page, so will another bond. But the other bond here will be, one will come out of the plane of the page, and the way we're going to show this is I'm going to represent this with this wedge. Okay, this means bond out of plane. Okay, so one bond is going to go out of the plane of the page, and the other bond will go into the plane of the page, which I'm going to show with this dashed wedge. Bond into plane of the page, and I'm going to show that here. Okay, so this has 4 electron groups, and we're going to just equate that with 4 bonding atoms. Okay, and if you wanted to look at this in terms of a plane, just to visualize this in a 3-dimensional structure, so here's our plane. I'm going to draw this out here. Whoops. Okay, so here's our plane, and one of the central atoms here, okay, and you're going to have 2 bonds in the plane of the page, so let's put one here, whoops, one here, and one here. Then the other bond here is going to go out of the plane of the page, and the way I'm going to show this is I'm just going to demonstrate that here. Right, so you got to imagine it coming out of the plane, so maybe I could just, okay, there you go. One will come out of the plane, and one will go into the plane of the page. Okay, so you would basically, maybe you could, it's kind of hard to see this, but, so think about this as a tripod, guys. Right, so think about this as a tripod, because you're going to basically have one bond that's going to be up here, and then something that looks like that, right? And it forms like a tetrahedron there, right? A tetrahedron is a triangular pyramid. So you got to think about this in terms of shapes, right? So it essentially forms a triangular pyramid, and you can draw these in 3 dimensions if you really want to, right? I think this is just enough when you're looking at a page, because they don't expect you guys to be artists, right? But that's essentially what happens. Like if you take this structure here and you try to visualize this in 3 dimensions, right, you're basically going to get a 3-dimensional shape like that. Good. So this actually does form a tetrahedron. That's why it's called tetrahedral. So it's really interesting. Anyways, the bond angle that you actually create here is 109.5 degrees, right? So all of these angles here, right, between the bonds, right, are basically 109.5 degrees. Okay, this is actually one of the most stable type of bond angles. That's why the tetrahedral geometry tends to be the most stable type of compound. Let's take a look at 5 electron groups. So we're looking at 5 electron groups. This is called Trigonal Bipyramidal. And what Trigonal Bipyramidal will look like, you'll have a central atom located here. You'll basically have a bond here, and a bond here, and this is going to be in the plane of the page, and they're all going to be 90 degrees apart, right? And then the other 2 bonds, one is going to come out of the plane of the page as such, and the other bond will go into the plane of the page. So this actually kind of gets a little bit more complicated. So you can see that there's multiple bonds that are located here, right? And for the most part, we're going to basically see 90-degree bonds here. So this is going to be 90 degrees. And we're also going to see 120-degree bonds here. Okay, so these are actually going to be 120 degrees. Right, so it's kind of hard to see this in 2 dimensions. And let's try to draw this on a plane just to kind of demonstrate this. So here's our plane. Okay, so this is our plane here. And we're going to have a central atom that's located here. Right, we're going to have a bonding atom here, here, and here. That's 90 degrees. And then you're going to have one that's coming out of the plane of the page. And that's one that's coming into the plane of the page. Okay, so it's kind of hard to see that. Maybe I could just draw that a little bit better. Right, maybe you could put that here a little bit. Okay, and you can see that this is 120 degrees, right? These are 90 degrees, right? These will also be 120 and so forth. So it's kind of hard to see this. The reason they call this trigonal bipyramidal, well, first of all, if you want to construct this, I'm just going to kind of draw it out here so you guys can kind of see it. So I really want you guys to appreciate the actual three-dimensional structure of this, right? We don't want to just memorize material. We want to try to understand it as much as possible. Right, I'm just going to draw it out here so you guys can see it. Right, one's going to come into the plane of the page, right? Into the plane of the page here. One is coming out of the plane of the page here, right? And in this case, if these guys were in the same plane, what you want to understand here is that these three, they form basically this triangle, and this forms a pyramid as shown here. Okay, so it's kind of hard here to demonstrate this, but these guys form a pyramid, right? Okay, so it kind of forms, it's basically two tetrahedrons on top of each other, right? You can see one tetrahedron up here and the other tetrahedron below, right? So it's like me taking two tetrahedrons and putting them, right, one on top, one on the bottom. So that's basically what trigonal bipyramidal looks like. Okay, so it's a little difficult to kind of understand. It looks kind of like a quartz, a diamond, almost, right, in that shape, right? But that's the idea, really. And there's going to be two bond angles here. So this is 90 degrees and 120 degrees. Okay. Now the next, or the last electron geometry that we're going to look at, we're not going to look at anything past 6 electron groups because it gets too complicated. If you wanted to take chemistry in university courses, you could explore this to a higher level, right? For the time being, we can stop at 6 electron groups, and this actually represents something called an octahedral electron geometry. Okay, so what octahedral will look like is we're going to have we're going to have a central atom here, right? We're going to have a bonding atom here in the plane of the page, bonding atom here in the plane of the page, and then we're going to have two bonding atoms that are going out of the plane of the page. Whoops, I forgot to switch colors here. Kind of got lost in the material. So two bonding atoms in the plane of the page, two bonding atoms coming out of the plane of the page, and two bonding atoms going into the plane of the page. Now if we draw this on a plane, I'm just going to erase this stuff here, right? If we drew this on a plane, you can imagine, I'm just going to draw it out here, but then we'll look at this in a larger, actually we'll do it here, right? If I drew this out here in the plane of the page, you can have a central atom here, right? You're going to have a bonding atom coming out here and here, right? And then you're going to have a bonding atom that's going to come out of the plane of the page, as shown, right? And then two that go into the plane of the page. Okay, and you can imagine that each of these guys are going to be 120 degrees, right? These will be 120 degrees, right? This here would be 180 degrees, right? So we have 120 degrees, 180 degrees, right? Some of these you'll actually see as having 90-degree angles, right? The one that's going in the plane of the page and the one that's going out of the plane of the page, this would be 90 degrees. Okay, so there's also 90 degrees as well, right? And if we were going to represent this in 3 dimensions, you can imagine this as two square-based pyramids placed one on top of each other. So I'm going to show you guys this. I'm going to draw two square-based pyramids. Okay, so let's create the scaffold here. Okay, so let's just do that here and there, and then here as well. So you don't really have to be an artist to kind of learn this stuff, guys, because that's why in your chemistry courses you're basically gonna be only expected to draw this in 2 dimensions. So you don't need to worry too much about that, right? So yeah, so that's the idea. So we basically have that, and then the central atom here will be located here, right? You're gonna have a bonding atom here. You're gonna have a bonding atom here, 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 and here, and one there. Okay, so you're basically gonna have something that looks like this, something that looks like that, something that looks like that. Okay, so you can think of it that way as well, right? In this case, I just flipped up these 2 bonds in the plane of the page, and then the other guys go out of the plane of the page, right? So you'd have to construct it according to that, right? So the score base would be these 4 bonds here, okay? But so you're gonna have to reorient this. You have to flip it upside down and make sure that it fits in the plane. However, so that's basically the idea, right? So these are the 5 electron groups and the 5 electron geometries that we are going to be looking at. And the electron groups are given a special name. The number of electron groups is given by something called the steric number n. Okay, so it's also known as the steric number, which tells you the number of electron groups. Okay, so keep this in mind, guys. And we're going to kind of explore all of these. Just going to rewrite that. We're going to explore all of these electron geometries. But specifically, we're also going to take a look at cases where we're actually going to see lone pairs. And when we do see lone pairs, it actually causes deviations in the electron geometry. And this actually creates something called an electron, a molecular shape, right? So there's different molecular shapes that can exist within electron geometry based on changes in the lone pairs, the number of lone pairs that are present, right? So let's take a look at some of these cases. We'll look at. All right, let's have a complete overview of the different types of electron geometries and molecular shapes that can exist for different molecular compounds. Okay, so these are basically, according to VSEPR theory, associated with the number of lone pairs that exist around a central atom, as well as the bonding atoms or bonding electron pairs that surrounds the central atom as well. Okay, so we stated earlier that the steric number is the number that's given to represent the total number of electron groups, right? So let's say we had 2 electron groups. Okay, so the electron geometry of 2 electron groups is what we generalize as linear. Okay, now when you have 2 electron groups, you can have 2 bonding atoms and 0 lone pairs, and this is the structure that we initially depicted, right? And I'm going to use red here as a central atom, so I'm just going to use the same the criteria, the same legend that we used before, right? And we stated that the bonding atom is bonded to the bonding atoms are bonded to the central atom in 180 degree fashion. Okay, so they're 180 degrees apart. Maybe you could, 180 degrees here, right? And the bond angle here was 180 degrees. And an example of this, we could demonstrate this using carbon dioxide. Okay, so carbon dioxide will actually look like this. And you're probably wondering, okay, so I demonstrated this geometry with a single bond, but single bonds, triple bonds, and double bonds basically appear the same way. We're only looking at bonding atoms as well as lone pairs. So that's why I kind of, instead of looking at bonding electron pairs, we can just look at bonding atoms. It basically means the same thing. Okay, so carbon dioxide is an example of a linear structure, a linear compound, linear structure for a compound, right? Now let's take a look at Now another example of linear, and this is not so common, but I'm just going to list it anyways because we will be looking at the structure of polyatomic ions. If we have a steric number of 2, we can also get linear if we have one bonding atom and one lone pair. And I'm going to show you guys this. It's basically going to be linear, but this time around we only have one bonding atom, right? So it looks like that, and you're going to see a structure like this. It's still going to be 180 degrees if you assume it's from here, right? However, we can't really represent an angle. If you looked at this as being your initial, this could still be 180 degrees. It's still kind of linear in a sense, right? So you'd still call it 180 degrees. Examples of this, and there's not too many examples, but I'm just going to point out cyanide, for instance, Cn -1 charge, right? Cyanide will actually resemble this structure. Now cyanide, it's a polyatomic anion, right? And its structure will actually kind of look like this. Well, this is the only real way that it forms a stable octet, right? The structure itself has to gain an extra electron to fulfill it, and this is essentially what the structure will look like. So you can see that the central atom, which would be the carbon here, right, has this one lone pair, right, and one bonding atom, which is the nitrogen, right? We said that the least electronegative atom is going to be the central atom. Okay, so this is really an exception. You won't tend to use this too much. Now let's take a look at if you have a steric number of 3. Okay, so if you have a steric number of 3 here, we're going to have an electron geometry that's called trigonal planar. Okay, so trigonal planar, and we looked at the general architecture where we had 3 bonding atoms and 0 lone pairs. Okay, so 3 bonding atoms, 0 lone pairs, this gives you the general architecture here. Will basically look something like this. Okay, so this is, and we're just going to draw this in 2 dimensions because I think I showed you guys what this would look like in a 3-dimensional scope, but if you guys still wanted some a general understanding of this, I would really recommend you guys to get a molecular kit, right? So using a molecular kit, you can kind of just play around with some of these shapes and really appreciate this stuff for what it is, right? So it's not too adequate to just memorize this. It's good to have a better understanding of it and visualize this. Okay, so this is going to give us 120 degrees here, right? And an example of something that's trigonal planar. Now this is actually more of an exception, but boron trichloride, right? Boron actually has a much more shortened octet, right? And boron trichloride will basically look like this. Okay, so just by drawing the Lewis dot structure, and maybe I could demonstrate this using a different color here. Okay, well, I'll just draw it as structural. Right, so boron trichloride will look like this. Okay, and this is 120 degrees, right? And you can draw its Lewis dot structure to determine that, right? But boron has 3 valence electrons, right? But that's what its VSEPR structure will look like. Now, the other case, we're still going to have trigonal planar geometry as long as we have 3 electron groups, right? And we said that the steric number n is equal to the bonding atoms plus the lone pairs, right? As long as we have 3 electron groups, n is equal to bonding atoms plus lone pairs. As long as we have 3 electron groups, it's still going to be trigonal planar. However, we can have 2 bonding atoms this time and 1 lone pair. So what 2 bonding atoms and 1 lone pair will look like is basically you're going to have a central atom here, you're going to have 2 bonding atoms here, and this 1 lone pair is going to exist within this orbital. Okay, so I'm just going to show that out here. Okay, so this is 1 lone pair on the central atom. It's always relative to the central atom, and this is our 1 lone pair. So it's going to be in this orbital. I know it looks like an alien or whatever, right? It looks kind of weird, but we're just drawing this in 2 dimensions, right? And This is actually given a special name, right? This is actually called angular bent V-shaped. Now, commonly people will call it bent, right? Angular bent V-shaped, look like this, and in this case, it has one lone pair on the central atom. Okay, now the bond angle here slightly deviates from the 120-degree architecture, and in this case, this is actually going to be less than 120 degrees, and this is actually going to be approximately 117 degrees. Sorry about that. Okay, so it's approximately 117 degrees. Okay, now you can just say less than 120 degrees. That would be perfectly fine. An example of this with one lone pair. Okay, so this one isn't too common, but we can look at the example of sulfur dioxide, right? And sulfur dioxide actually kind of looks like this, right? You guys can kind of work out its Lewis dot structure and structural, but there's essentially going to be a lone pair of electrons here, right? Okay, and this is actually angular bend V-shaped, right? So it's gonna model this structure, right? So the bonding atoms is the oxygen, the central atom is the sulfur. So we can use these templates to look at each of these shapes, right? And the last variation of trigonal planar, maybe I could just kind of fit this in here. I'm just gonna erase this portion, right? Didn't really conserve space too much, right? And then last set here that we can look at. Trigonal planar electron geometry. This time we're going to have one bonding atom and basically two lone pairs. Okay, and technically this is going to be linear as well. Okay, so it's going to have something that looks like this, and it's going to be bound to that. But this time it's going to have three lone pairs, right? So if it's three lone pairs, what we're going to see here is, well, sorry, two lone pairs. We're going to see one here and one here, right? Okay, so this one doesn't seem as like it's too common. And you would expect this to be linear. So you could say this is actually going to be 180 degrees. This isn't too common. You won't really see this, right? But this one isn't as one isn't common at all, so we can't really come up with an example for this. So you guys don't need to consider this one, right? You can omit this one by default because I can't think about any example of a compound that can actually have this architecture and also be stable, right? So don't worry about this last one, guys. It's not common at all, right? But the ones that you want to look at in terms of linear and trigonal planar geometry and shape is the four above. Okay, so the next thing we're going to look at is the tetrahedral geometry, which is going to be associated with the steric number of 4, right? There's 4. Okay, so let's take a look at 4 electron groups surrounding a central atom, right? We looked at the number of electron groups that's being represented by the steric number, and you can denote the steric number as n, right? So in this case, we're just going to be looking at the tetrahedral electron geometry. This is probably one of the most important type of electron geometries. It's really common within many compounds, especially molecular compounds, because these tend to be the most stable. The 109.5 degree bond angle is the most stable bond angle for molecular compounds, right? Because it actually allows for ample amount distance to facilitate enough bond strength, but also minimizes electron interactions, right? So these electron interactions which cause repulsion, these are called steric interactions. So this bond angle, this 109.5 degree bond angle, is actually the most effective in doing so, right? So it reduces all of this, the steric strain, right? The strain that the repulsion will create. So let's take a look at the base level of tetrahedral. So in general tetrahedral electron geometry, we'll have 4 bonding atoms and 0 lone pairs, right? And when we have 4 bonding atoms and 0 lone pairs, the molecular shape will just kind of look like this, right? I'm going to draw this in 2 dimensions, but you guys can think about this on a plane for 3 dimensions, right? And let's just let's draw this on a plane actually. But basically, you're going to have 2 bonds in the plane of the page. Okay, so let's draw a plane here so you guys can visualize this. Okay, so maybe we can move this a little bit here. Okay, so you're going to have 2 bonds in the plane of the page as shown. So one here, let's say one was here, and then one bond will come out of the plane of the page, so it'll just come upwards, and the last bond will go into the plane of the page. Okay, and the reason we call this tetrahedral is because it does form a triangular pyramid, as I showed you guys earlier, right? We don't want to look too much on the 3 dimensions on a page. I want you guys to kind of play around with your molecular kit and get that done. Now, in this case, the bond angle here we said was 109.5 degrees, right? So this is your stable bond angle. And an example of a molecule that's tetrahedral, let's take a look at methane. So methane looks like this. Okay, so there's no lone pairs here, and it follows that tetrahedral geometry. Now, carbon being the central atom, hydrogen is never a central atom. Now, let's take a look at if we have a lone pair this time. We have 1 lone pair, and we need to have 3 bonding atoms. And the main idea here is that the bonding atoms plus the lone pair should give us the total number of electron groups, or also known as the steric number, right? So an example of 3 bonding atoms and 1 lone pair, what that's going to look like is you're going to have 1 bond in the plane of the page, 1 that's going out of the plane of the page, and 1 that's going into the plane of the page, right? So let's kind of construct our plane here. Okay, maybe I should have constructed the plane first, right? This is going to go into the plane of the page. Now it's kind of hard to see this, right? So it's going to go into the plane of the page. You can't really see it. And the non-bonding electrons, a lone pair, is actually going to be in the plane of the page. Okay, so it kind of takes the place of the bonding atom that's not there. Okay, so it's still going to be in the plane of the page, which you can see there, right? And the bond angle here is going to be slightly less than 109.5 degrees. It's actually going to be approximately 107 degrees. Okay, this this electron geometry actually has a slight deviation in its molecular shape, and this molecular shape is given a special name. It's actually called Trigonal Pyramidal. Okay, so you guys actually have to pyramidal. Whoops. Where's my spelling there? You guys actually have to memorize these molecular shapes. So this is actually trigonal pyramidal, right? And it has this, it's less than 109.5 degrees, and you can actually write less than 109.5 degrees. It's perfectly correct. It's approximately 107 degrees. Example of this is our good friend ammonia. Okay, so ammonia kind of looks like this, right? There's a hydrogen here, right? There is 1 bond that's coming out of the plane of the page, 1 that's going into the plane of the page, and there is going to be a set of lone pairs. And I'm just drawing this in 2 dimensions, guys, right? But you guys can visualize this in terms of a plane if you wanted to. I just wouldn't have time to kind of go through all of this to do that, right? But maybe when we look at some examples, we can kind of illustrate this. Okay, so now let's take a look at another scenario where this time we actually have 2 bonding atoms and 2 lone pairs. Okay, so if we have 2 bonding atoms and 2 lone pairs, what we're going to see here is, if I draw a plane here, right, we have a central atom here, right? It's going to have 2 lone pairs, so they're going to be in the plane of the page. Shown there. And then we're going to have a bond that's going out of the plane of the page, and a bond that's going into the plane of the page. Okay, actually in this case, what we're going to do here is we can illustrate this where the lone pairs are actually coming out of the plane of the page. So the lone pairs actually, one will come out of the plane of the page like so, and one will go into the plane of the page like so. Okay, so this is I kind of switch colors here so you guys can see it. There's lone pair here and lone pair here. One comes out of the plane of the page, one goes into the plane of the page, and in this case, I'm just gonna, because it's gonna conflict with our legend, right? And then the other two bonds will be in the plane of the page as shown, right? And the angle here is going to be less than 109.5 degrees. Now this specific molecular shape is given as angular bent V-shaped. Okay, so we looked at this earlier, but this is another angular bent V-shaped, and you can just call it bent if you really want to, right? And the bond angle here is going to be less than 109.5 degrees. It's actually going to be less than 107 degrees. It's approximately 104.5 degrees. An example of this, and probably the most common example, is water, right? H2O, right? So H2O will basically look like this. The oxygens are going to be coming out of the plane of the page, right? And in this case, we have a hydrogen here and a hydrogen here, right? And so this angle here is 104.5 degrees. Okay, so that's a really important one to know. And the last example of tetrahedral that we're going to look at, there actually is only one more that's relevant, right? So I'm just going to erase this. Sorry, guys. Right? The last example that we're going to look at here is basically, let me change colors. We have three lone pairs, one bonding atom, and there's not too many examples of this, but this is also another example of linear, right? Where you're basically going to have a central atom shown here and a bonding atom shown here. It's going to be in the plane of the page, right? Okay, it's going to be in the plane of the page, and we're essentially going to have three valence electrons, right? So now the valence electrons, one can be in the plane of the page, one is going to be out of the plane of the page, and one's going to go into the plane of the page, right? So there's three valence electrons here, here, and here, right, in these orbitals, right? And in this case, you're going to assume that we're just looking at the bonding angle. It's still going to be 180 degrees, right? At least use a different color for that, but this is still going to be 180 degrees, right? So it's going to be 180 degrees, and an example of this, you could look at hydrogen chloride, for instance, right? Hydrogen chloride will look like this, right? And you're going to see a bond here, right? And in this case, the chlorine here is the central atom, right? So that's the idea. There aren't too many that follow this structure of tetrahedral, but this is basically what we call linear. Okay, so we looked at three different molecular shapes of tetrahedral that are variations of this electron geometry due to the fact that we have the presence of lone pairs. All right, so it's very important to memorize these guys in terms of their bonding atom as well as lone pairs, and just to kind of summarize each of their molecular shapes. Right, I'm just gonna kind of look at it here. We can summarize it here if you guys want, without considering the original tetrahedral shape. The three shapes that we did look at, and I can just kind of separate it here. Three shapes that we looked at included three bonding atoms, one lone pair. We had trigonal, pyramidal, right? And we looked at a bond angle of 107 degrees, and you guys can look up here. We also looked at two bonding atoms, two lone pairs. This was called V-shaped, or we can call it bent, right? We can call it bent, right? And it's 104.5 degrees, right, bond angle. And we looked at the case of linear, which had one bonding atom, three lone pairs, 180 degrees. And we looked at some of these examples, right? The one that was trigonal pyramidal was ammonia, so NH3. The one that was bent was water, and the one that was linear was hydrogen chloride. Okay, so kind of memorize this, guys. Memorize the linear structure, the linear geometry, the trigonal planar geometry, the tetrahedral geometry. And the next thing we're going to be looking at is 5 electron groups. The steric number is equal to 5, and this electron geometry will be called trigonal bipyramidal. Okay, so let's continue our discussion of VSEPR structures, and let's take a look at, this time, structures with a steric number of 5. So the steric number 5 represents 5 electron groups, and the electron geometry for a steric number 5 is called trigonal bipyramidal. And what trigonal bipyramidal will look like, the central atom is going to have 3 bonds in the same face of the plane, right? In the same plane of the page, right? And basically one that's going to go out of the plane of the page, and the other bond that goes into the plane of the page. And the bond angle between the bond that's in the plane versus out of the plane is 120 degrees, and the bond angle that's in the plane and going down below the plane is also 120 degrees, and these guys are going to be 90 degrees to each other. Okay, so the bonding atoms here are going to have, and if we're just looking at the generic electron geometry, if we have 5 bonding atoms and 0 lone pairs, the molecular shape will also be trigonal bipyramidal. And I'm just going to draw this another way here. I'm just going to use the plane. So say this is the plane of the page. Okay, and we're going to have one species in the center, right? One bond here, one bond here, one bond here, and the other bonds that are going to go out of the plane of the page. So one that will basically go out this way, right, and one bond that's going to go into the plane of the page, like so. Okay, so there's going to be one there, one here, and then the ones in the plane. Okay, so the bond angles associated, we kind of alluded to earlier, just 90 degrees and 120 degrees. And an example of this, and once again, most of these guys will violate the octet rule. We can take a look at PCl5, right? So this is phosphorus pentachloride, and in this case, the potential structure of this, if we draw out the plane here, right, will look like as shown. There's one chloride in the plane, chlorine in the plane, chlorine in the plane, one that goes out of the plane as such, and one that goes into the plane like as such. Okay, so that's the structure for trigonal bipyramidal, but we can still have the trigonal bipyramidal electron geometry. But this time we have an additional lone pair. So let's say we have one lone pair and 4 bonding atoms, right? So the geometry still kind of looks like this, right? But now, because we have this one lone pair, it's going to deviate the angles, and specifically one of these bonds are taken up by the bonding the lone pair, right? So the lone pair now is going to constitute one of the bonds, and the lone pair acts as such, right? And the lone pair will cause electron pair repulsion. So look at what happens now. So you can see that one of these bonds here are being picked up by the lone pair, and now we have a structure that kind of looks like this. And this is just basically me drawing this in 2 dimensions, right? And this structure here is called seesaw. Okay, so seesaw, they're actually going to have a 180 degree bond angle here, right? So you're going to have 90 degrees 180 degrees, and 120 degrees. And you should also see 180 there as well, right? And this lone pair just kind of is in the presence of this previous bond, okay? So an example of seesaw, we can take a look at this. Let's take a look at sulfur tetrachloride, SCl4, okay? So SCl4, the Lewis dot structure, well, the structural diagram for this guy is going to kind of look like this. Okay, and if we draw this using our VSEPR notion, okay, so here's my plane, right? Sulfur's in the plane, there's a chlorine here, there's a chlorine here, and there's also a lone pair in the same end of the plane, and then one bond is going to go out of the plane as such, so it's going to go above the plane, right? And remember that all of these guys have lone pairs, the chlorine. Okay, so you can kind of just draw that in. And then one bond for chlorine goes into the plane as shown, like that. Okay, so that's basically the structure, and then you can kind of look at some of the bond angles being created. Okay, so this is what we call seesaw. This is the molecular shape, right? In the first scenario, because there were no lone pairs, it just matched the electron geometry, and it's called Trigonal Bipyramidal, right? So, an A on there. Okay, so it's called Trigonal Bipyramidal. And let's take a look at another structure here. Okay, so steric number 5, the electron geometry is still Trigonal Bipyramidal. So we still have this structure, right? So we still have this structure where the central atom is located here, right? One is here, one is there, one is there, right? And then one bond is going out of the plane. Okay, so as such, okay, so one bond is going out of the plane like that, and one bond is going into the plane like this. Okay, and basically in this case, but now we're going to have, instead of having 4 bonding atoms, we're going to have 3 bonding atoms and 2 lone pairs. So 3 bonding atoms and 2 lone pairs, it basically will mimic something called T-shape. Okay, so this is what T-shape look like, and it's just kind of like what the name sounds like. Okay, so here's your central atom. Okay, so this is called T-shaped, right? And basically all of these angles are going to be 90 degrees to each other, and this would be 180. Right, so 90 degrees and 180 degrees, right? An example of a molecule that's T-shaped, and also there should be 2 lone pairs here. Maybe we should shift this down a little bit so you guys can see this. Right, so let's redraw that. Okay, central atom, say that these are the lone pairs. Okay, so you can see that the lone pairs kind of take up the space of the bond that's going out of the plane and into the plane, and then there's going to basically be these bonds here. Okay, so this is the T-shaped molecule, right? And you're going to have 90 degrees and 180 degrees. And an example of T-shaped, we can look at phosphorus trichloride, right? And phosphorus trichloride here would kind of look like, right, so there's phosphorus here, right? And you're going to have these bonds in the plane, right? And then basically one bond here of chlorine. Oops. Chlorine here and a chlorine there. Okay, so this is what the structure will look like, and this is basically everything's in the plane, but the 2 lone pairs will be kind of out of the plane, right? So this basically has a generic structure of 3 bonding atoms and 2 lone pairs, right? So these are just some examples of the Trigonal Bipyramidal electron. Okay, so looking at the steric number 5, the electron geometry being Trigonal Bipyramidal, which we said that the structure will look like, right, bonds out here. And remember, these are 90 degrees apart from each other, right? And we should have bond going out of the plane of the page and bond going into the plane of the page, right? So there should be 5 bonding atoms. In this case, we need to add the bonding atoms and lone pairs will add up to the steric number, right? 5 electron groups. So we've looked at where we had 4 bonding atoms, 1 lone pair, 3 bonding atoms, 2 lone pairs. Now we're going to look at 2 bonding atoms, 3 lone pairs. And this molecular shape is called linear. What this looks like here, right, is basically when you have, excuse me, when you basically have a central atom, right, and you're going to have 3 lone pairs on that central atom, so it should look like that, right? So you have 3 lone pairs on the central atom, and then basically the 2 bonds would just be 180 degrees. Okay, so it's just 180 degrees. Okay. Put another way, the structure would basically look like this. Okay, so you should have in the same plane, you know, and then you can think about these lone pairs as kind of going below and above the plane of the page, right? So the example here, something that's linear could potentially would be xenon difluoride. So if we look at xenon difluoride, all right, if I just look at the Lewis dot structure, you can notice that this normally has stable octet, right? And then one is here. Let me just show this using a different color so you guys can kind of see it. Right. So xenon is going to donate one of its electrons to each fluorine to create a stable octet, and fluorine is a halogen, so you should expect it to kind of look like that. Right. Now, using this structure here, right, we would expect, and xenon has these 3 lone pairs, right? So 1 lone pair here, 1 lone pair there, 1 lone pair there, right? So if we look at this, xenon, there's a lone pair here, lone pair here, lone pair here. Okay, and then this is going to be, the 2 fluorines would be linear relative to each other. Okay, and yeah, that's the linear structure. Okay, so those are the geometries. Those are the, I think we looked at 4 cases of molecular shapes of 5 electron groups. Okay, so I think a really quick way of summarizing this is we're looking at steric number, bonding atoms, lone pairs, right? We have a steric number of 5 bonding atoms. If we have 5 bonding atoms, 0 lone pairs, this was trigonal. This was the original trigonal bipyramidal. Right? If we have 4 bonding atoms, 1 lone pair, right? Then this is called seesaw. If we have 3 bonding atoms, 2 lone pairs, this is called T-shaped or T-structure, same thing. And if we have 2 bonding atoms, 3 lone pairs, then this is known as linear. So this is what I want you guys to kind of understand. These are the molecular shapes of the electron geometry, Trigonal Bipyramidal. Okay, so that's just to summarize everything we've looked. Okay, let's take a look at a steric number of 6. So we have 6 electron groups, right? So in the 6 electron groups, they're called octahedral. And generically, the electron geometry will kind of look like this, right? So we're going to have 2 bonds in the plane of the page, but we're going to have other 2 that are out of the plane of the page and 2 that are going into the plane of the page. Now, when you do take further chemistry courses, you will look at these bonds as axial and equatorial. For the time being, we'll just look at them as out of the plane of the page, into the plane of the page. But the axial and equatorial just refer to a 3D network that are in the, if you're looking at a sphere, right, basically a region of electron density, equatorial would be basically the equator of that sphere, and axial would be perpendicular, like the longitude of that sphere. Anyway, that's not too important. We'll just look at it this way for the time being. Bonding atoms, there's 6 bonding atoms, 0 lone pairs. This is the generic octahedral molecular shape which matches the geometry, right? And if we wanted to design this in terms of a plane here, right, so I'm just going to do that in terms of a plane. So this is our plane, right? And we can notice that this is our central atom here. Okay, so 2 are going to be in the plane of the page. 2 will basically go out of the plane of the page as shown. And then 2 will go into the plane of the page as shown. Okay, so that's the octahedral. And the bond angles for this, these are actually purely going to be 90-degree bond angles, right? So they're just going to be 90-degree bond angles. So all the bonds are basically 90 degrees to each other, right? So you're gonna understand that, and the one way you can really look at this is that we know that in 3 dimensions there's the x, the y, and the z plane, right? So opposite of that, you would expect bond here, and a bond here. So that's essentially what it's going to really look like, right? So basically, for our discussion currently, the axial and equatorial regions would basically be these guys. So these would be, if you look at a sphere, these would be equatorial, and the axial regions would basically be the top halves, right? So these would be axial. Okay, and collectively this would form a sphere. But you can, in a 2-dimensional setting, you can draw like this, right? Example of this structure, we could use, let's say we have xenon hexachloride, right? Actually, sorry, not xenon hexachloride. Let's do sulfur hexachloride. Sulfur hexachloride, right? Sulfur hexachloride would have a structure that looks like this. For the time being, okay, we're just going to stick to our line structure, right? But we'll look at axial equatorial for future chemistry discussions. Then let's take a look at if we had 5 bonding atoms and 1 lone pair, right? So we're going to have a steric number of 6, and this is also still octahedral. So once again, we're still having this general structure here. Because of this lone pair, it's going to cause the angles to deviate a little bit. Right? Because we have a single lone pair, it's going to cause the angles to deviate a little bit. And what I'm going to do here is I'm going to replace this with a lone pair. And this is given a special molecular name, right? So now we're going to have a lone pair here, right? And then we're going to have basically 1 bond straight down, 2 bonds that look like this, and then 2 that are going into the plane of the page. Now this is called square pyramidal. Okay, and now the angles are going to be 9 degrees, but because of the lone pair here, this is going to be slightly less than 90 degrees. So we're going to have 90 degrees and less than 90 degrees. It could be like 86.4 or something, right? So that's an example. Square, and this is called square pyramidal. That's the molecular shape. Example of square pyramidal is going to be bromine pentafluoride, which will basically look like, if we drew our plane here. Okay, so bromine here, right, it's going to have a lone pair, right? It's going to have a fluorine here. Okay, so there's a fluorine there. Maybe just let me redraw that really quickly. Okay, so there's a fluorine here, right? And then there's going to be 2 fluorines here, and 2 going into the page here. Okay, so bromine pentafluoride would work in that sense, and you would basically put down its valence electrons for the fluorines, right? So I'll let you guys do that. Anyways, and the last structure that you guys are required to know, you have 4 bonding atoms and 2 lone pairs, This is still electron geometry of octahedral. Oops. Okay, so the electron geometry is still octahedral, but this is going to be called square planar or square base planar. Okay, and square planar, technically it just kind of looks like everything's in the plane of the page to an extent, right? But to go out of the plane of the page, they still create this plane, and then to go into the plane of the page. Okay, so one's two below, two above, and they create their own plane, really, right? So what square planar will kind of look like, say we have their angles here. So an example of this is xenon tetrafluoride, right? So in this case, you would see xenon would have two lone pairs, and then basically fluorine here, fluorine here, fluorine here, and fluorine here, right? So this is the structural diagram. So let's take a look at this in terms of the VSEPR. So this is our plane. Here's xenon, right? And basically we're gonna have two in the plane of the page. So let's say it's here, and then one bond that goes out of the plane of the page, fluorine, another bond that goes out of the plane of the page, fluorine, one that goes into the plane of the page, and another that goes into the plane of the page. So it looks like that, basically. So this is the square planar, right? So these are our octahedral structures. Okay, so let's make a summary of the VSEPR structures that we looked at, just to memorize, right? So that you can use this method to memorize, but I'm going to use N for the steric number, Ba for bonding atoms, and Lp for lone pairs, right? And remember, the steric number is the total number of electron groups, right? Ba here is the bonding atoms, Lp here is the lone pair. And I'm really concerned about the molecular shape, right? So what I'm going to do is I'm just going to start from steric number of 2. So we have 2 bonding atoms, 0 lone pairs. This structure is linear, right? And basically the electron geometry, we looked at it like this, right? If we have 3 bonding atoms, we can have 3 bonding atoms and 0 lone pairs. Sorry, if we have 3 electron groups, we have 3 bonding atoms, 0 lone pairs. This is trigonal planar. I mean, this also mimics the electron geometry. Okay, but we can also have, within its molecular shape, we can also have electron geometry of 3, 2 bonding atoms, and 1 lone pair, right? So this actually indicates angular bent V-shaped. And we said that trigonal planar here was 120 degrees, right? Linear was 180 degrees. So angular bent V-shape should be less than 120 degrees. Okay, so I'm just kind of summarizing this for you guys so you can just memorize this. Then we looked at electron geometry. You know what, I'm going to use yellow for all the electron geometries. We looked at electron geometry of tetrahedral, which contained 4 electron groups, and there was 4 bonding atoms, 0 lone pairs. Right, tetrahedral, which basically looked like this. Right, 2 bonds were in the plane of the page, 1 was out of the plane, 1 was going into the plane. Bond angle was 109.5 degrees, right? And we looked at some variants of that. If we had 3 bonding atoms, 1 lone pair, this was something called trigonal pyramidal. Okay, so this is trigonal pyramidal, and in this scenario, we're going to have, so we know that tetrahedral was 109.5 degrees. Well, trigonal pyramidal here is going to be less than 109.5 degrees. So that's why you can write here, and just kind of recall that the molecular shape, for one of the bonds we're going to have a lone pair, and then you can notice that the other guys persist, right? And this is similar to when we looked at angular bend V-shaped. One of the bonds was a lone pair, and then the central atom has basically a lone pair. Okay. And so we looked at trigonal bipyramidal, and trigonal pyramidal, and we also looked at two bonding atoms, two lone pairs, and this was called angular bent V-shaped. Or you can call it V-shaped or bent, right? In this case, we have two lone pairs now. So now what's going to happen here is we have the lone pair here and the lone pair here, and this was also less than 109.5 degrees, and this will suffice for the most part. Okay. Then we also looked at electron geometry of trigonal bipyramidal, and for trigonal bipyramidal we had 5 electron groups, 5 bonding atoms, and 0 lone pairs, right? And we say that the structure kind of looks like this. Okay, and then one bond was out of the plane of the page, one was in the plane, and this was 90 degrees and 120 degrees. Okay. And then we looked at some of its variants, right? If we had 5 bonding atoms, if we had 4 bonding atoms and 1 lone pair, right, and this was called seesaw, so it looked kind of like that. There's a lone pair here, one going out of the plane, one goes into the plane. Okay, so this was called the seesaw. And once again, I don't name this, guys, you have to just memorize it, right? And you can say that the angles are slightly less than 120 degrees and less than 90 degrees, right? Then we also took a look at 5, 3, and 2, and we stated that this was called T-shaped, right? And T-shaped basically looked like this, where you'd have 2 lone pairs, right? And then each of these bonds were 90 degrees, right? And then we also had 5, 2, and 3. We have 2 bonding atoms, 3 lone pairs, and this was called linear. Linear was fully 180 degrees, right? And we had these 3 lone pairs in these orbitals on the central atom. Okay, so we looked at all of that, right? So that was up to 5. And then what we want to do here, I'm just going to make some space here. We also looked at 6. Okay, and this was called octahedral. Okay, and octahedral had these 2 bonds in the plane, 2 bonds out of the plane, and then 2 bonds going into the plane. Okay, and the bond angles here were 90 degrees. Right, so all of these are 90 degrees apart from each other. And then we looked at some variants of octahedral. Just gonna do them here. Maybe we can separate them. Right, so we looked at the variants of octahedral, where we had 5 bonding atoms, 1 lone pair, and in this case we had something called square pyramidal. Okay, so this is called square pyramidal. Okay, and the angles were less than 90 degrees and 90 degrees because of the lone pair. And then the last case we had 6, 4, and 2. We had something called square planar. So 1, 2 are going out of the plane. There's a lone pair here, lone pair here, and then 2 are going into the plane as shown. Okay, so this was called square planar. Okay, so those are basically the molecular shapes that we looked at, right? So I would say memorize these guys, right? So I'm just going to underline all the molecular shapes that we looked at, right? So you need to memorize all of these molecular shapes, right? And some of the molecular shapes coincide with the electron geometries, right? So try to find a way to memorize all of these. It's going to be really important for future studies of chemistry, right? Although we looked at this on a very surface level, right? In terms of its three-dimensional geometric structure, knowing this right now is going to help you for future chemistry courses, like if you take this in post-secondary, for instance, right? So also know square pyramidal and square planar. We'll stop at the 642 mark, and you guys can memorize this condensed structure that I demonstrated out here. Okay. Alright, for the following compound, describe its electron geometry and molecular shape regarding VSEPR. So we're going to use we're going to figure out the VSEPR structure of this compound. And this molecular compound is boron tribromide. So if we're looking at boron, we know that boron is going to have an atomic number of 5, and its electron configuration is 1s2, 2s, 2, and 2p1, right? And the valence shell here is going to have 3 valence electrons. So boron is going to have a Lewis dot symbol of 3 electrons. Bromine, in this case, bromine is a halogen. So bromine is a halogen because it's found in group 17. So we know its valence shell is going to comprise of 7 valence electrons, right? And the atomic number of bromine is 35. So if you guys wanted to figure out the electron configuration, well, this would basically be 1s2, 2s2, 2p6, 3s2, 3p6. From that, we go from 4s2, 3d10. Okay, so that's 30 electrons. And then we go 4p5. Okay, so the valence shell here is the 4th energy shell, right? And we're going to have 7 valence electrons. Okay, so now that we understand that, what you want to do here is let's figure out its Lewis dot structure. So a really quick way of figuring out its Lewis dot structure, we can use this equation. Total number of bonds is equal to the total number of electrons per stable octet minus the total number of valence electrons divided by 2. Right, so I'm going to create a chart here just to kind of organize this. So this is boron, this is bromine, right? Bromine has 7 valence. Right, I'm going to write down the total number of electrons you'd find in a stable octet. You have to note that this is kind of associated with Bohr-Rutherford's structure, right? So we need to kind of look at the octet rule here, but we can understand that the octet rule is, in some cases, it's violated because of the fact that quantum mechanical model, but also because there is a lot of exceptions here. We'll show you another method later on called formal charges that will help you to draw these structures a lot easier. For the time being, this will suffice. So the total number of electrons in the stable octet for boron here should be 8. For bromine, there should be 8 as well, but there's 3 bromines. Right, so I'm going to multiply this by 3, and you're going to get 24 plus 8, that's 32 electrons. Now for the total number of valence electrons, boron is going to have 3 valence, and bromine is going to have 7 valence, but there's 3 bromines, so I'm going to multiply this by 3. So you get 21 plus 3, that's 24, right? So the total number of bonds here is basically 32 minus 24 divided by 2, which is basically 8 over 2, which is 4. So there should be 4 bonds in this structure, right? So there should be 4 bonds in this structure. However, boron, in this case, would be the central atom. And boron actually has a smaller octet, so it doesn't violate the octet rule, right? It has a shortened octet, because it only needs 3 electrons. It only has 3 electrons, so it wants to lose all 3 electrons, right? Boron is your central atom because it's the least electronegative species out of in comparison with bromine, right? So this is a violation of the octet rule. So although you should see 4 bonds, there won't be 4 bonds here. I'm going to show you guys this when we draw this Lewis dot structure out. Boron has 3 electrons, and it only has 3 valence electrons, and it can only provide 3 electrons. Sorry, it can only provide 1 electron to each bromine that comes in. Now the bromines, the central atom tends to act as a good host for the bonding atoms. Okay, so this is essentially what the Lewis dot structure looks like. Okay, so you can see that this is a shortened octet, right? So this is a violation of the octet rule because although the bromines all have access to the shared network of electrons and they form stable octets, you can see that boron, and I'm just going to highlight that in lime green here, boron has a shortened octet. It only has access to 6 electrons, right? So this is an exception to the octet rule. So for the most part, this equation won't really help us too much. You should see one less bond. And in the structural diagram, each bonding pair of electrons constitutes a single bond. So using the central atom here, we can write that the structural diagram should look like as follows, right? So this is what the structure would look like. Okay. So this is your structural diagram. So this was your Lewis dot structure. This is your structural diagram. Now the next thing we want to consider here is, what is this molecule's electron geometry? Well, we have 3 bonding atoms, right? With 3 bonding atoms, we have 0 lone pairs. So if we have 0 lone pairs, 3 bonding atoms, we can understand that this has a steric number of 3. Steric number meaning the total number of electron groups is 3. So this tells us that our electron geometry is going to be trigonal planar. Okay, so the electron geometry is trigonal planar, and a really quick way we can figure out the molecular shape, I tend to do this out where I have the steric number to the far left, and then I use these hyphens, these lines to separate the steric number from the bonding atoms and the lone pairs. You can look at this condensed notation to memorize this stuff. So that the steric number here is 3, the number of bonding atoms is 3, and there's 0 lone pairs. This constitutes an electron molecular shape of also trigonal planar. So when there is 0 lone pairs, for the most part, usually the electron geometry and the molecular shape will coincide, right? And our molecular shape is trigonal planar. Well, if we're constructing trigonal planar, the central atom would be here, and the bonding atoms, I'm just going to do these dark black circles here, or dark blue circles, the bonding atoms will form 120 degrees in plane bond to the central atom. So this is your central atom, and these are your bonding atoms, right? And they're going to be in the same plane as the central atom. So technically the central atom here is the boron, so technically our structure should kind of look like this. Okay, so this is the molecular shape. Okay, and there's a 120 degree bond angle, and the molecular shape is also trigonal planar, right? And like we said earlier, that this should be in the same plane, right? So if this is our plane here, this is our plane, right? The bond here, the bond should be in the same plane. Okay, so that's basically its 3-dimensional structure. So it's really important. In order to design the VSEPR structure, you need to cycle from the Lewis dot structure, structural, and then eventually get to your VSEPR. And this equation does help with that analysis. Alright, for the following compound, describe its electron geometry and molecular shape regarding VSEPR. So we have CH2F2, right? So this is actually difluoromethane. I'm going to show you guys what this will look like. Let's start with designing the Lewis dot structure. Or constituent atom, there's carbon, there is 2 hydrogens, and there is 2 fluorines, right? I'm going to use this equation. The total number of bonds is equal to total number of electrons in stable octet minus total number of valence electrons divided by 2, right? So using this equation, I'm going to create a chart here. So we have carbon, which has 4 valence electrons, hydrogen, which has 1 valence electron, but there's 2 of them, and we also have fluorine, which has 7 valence electrons because it is a halogen, right? And there's also 2 of these guys. Okay, and what we're going to do here is we're going to write down its total number of electrons for stable octet, total number of valence electrons. So total number of electrons for stable octet for carbon, we need 8. For hydrogen, we need 2, but there's 2 of them, so 2 times 2. And for fluorine, we need 8, but there's 2 of them, so 8 times 2. So if I add these together, we have 4 plus 8, which is 12, plus 16, which is 28. Okay. Total number of valence electrons for carbon, there is 4. For hydrogen, remember that there are 2 hydrogens, right? There is going to be 1 times 2, and for fluorine, there is 7 times 2. So if I add this together, I get 14 plus 2, which is 16, plus 4, which is 20. Then total number of bonds here is equal to total number of electrons per stable octet, 28 minus 20 divided by 2, and this is going to give us 8 over 2, which is 4, right? So there should be 4 total bonds in this structure, and a potential layout of this, if we think about this, we could construct, one of our central atoms here. Well, our central atom has to be carbon. Hydrogen is never a central atom, and fluorine is the most electronegative out of these 3. So in this case, a potential layout here could look like this. Okay, I'm going to demonstrate this using different colors to show the bonding architecture. We should have 4 single bonds, right? Because there's 4 bonding atoms. So carbon, I'm just going to show its electrons in blue, right? Each fluorine needs to donate 1 electron to receive 1 electron, assuming that there are normal covalent bonds. Now you can see that the fluorines are happy, right? And we can see that the hydrogens will donate 1 electron to receive 1 electron, so they're happy. So now everything here has a stable octet. So you can kind of compare this, right? All of these guys have a stable octet. Okay, and if we wanted, so this was our Lewis dot structure. If we wanted to convert this into our structural, we can think about our structural to look like this. Okay, and you can notice here that the central atom has no lone pairs. So now we have 4 bonding atoms, 0 lone pairs, right? And this tells us that we have a total of 4 electron groups. Okay, so the steric number n is 4. So the steric number n is 4. We know that the electron geometry is going to be tetrahedral. Now, because we have, if we look at this as steric number, bonding atoms, lone pairs, we have 4 electron groups, 4 bonding atoms, 0 lone pairs, and as a result, we should also have a molecular shape of tetrahedral as well. Okay, so what does tetrahedral look like? Well, tetrahedral, central atom, I'm just going to use this open circle, 2 of the bonds that is created from the central atom, 2 bonding atoms, will have a bond of 109.5 degrees, right? The other bond will be out of the page. We're going to show this as a wedge, and the last bond is going to be into the page. We're going to show this as using a dashed wedge. Okay, so put that in this way. This is what our structure will look like, right? Using the carbon here, we're going to have a bond with the hydrogen in the page. Central atom is carbon, so another hydrogen in the page, and then let's say this fluorine is out of the page, and it doesn't matter where you guys position each of these bonding atoms, because we know that a single bond has free rotation around the bonds, right? So these guys can rotate freely, and we also have a fluorine that's going in the page. So I'm just going to draw a plane out. So the angle here is 109.5 degrees. Okay, so I'm going to draw a plane out to show you guys what that would look like. So if I draw out a plane here, whoops. Okay, so this is the plane, just a flat surface. This is the plane. Then we have the carbon to hydrogen bond in the plane of the page, the other hydrogen bond in the plane of the page. This angle here is 109.5 degrees, right? We also have a bond that goes out of the plane of the page. And so let's say that this is going out of the plane of the page, it's coming out this way, right? And this is the fluorine, and one that goes into the plane of the page. So it's going to be below the plane of the page. It's kind of hard to see this. It would be easier if you guys had like a molecular kit, right? Just gonna highlight this is the flat edge of the plane, right? But that's really the idea, guys, right? So this is basically what tetrahedral will look like, right? So the VSEPR structure of difluoromethane, which is this, is going to be tetrahedral. Okay, let's predict the VSEPR structure of the molecule sulfur tetrafluoride, right? So this is sulfur tetrafluoride. So I'm going to look at the total number of bonds here. Total number of electrons stable octet minus total number of valence electrons over 2, right? And in this case, we have sulfur, which has 6 valence electrons. Fluorine, which is a halogen, it has 7. There's 4 fluorines, and then total number of electrons in the stable octet here, total number of valence, this guy will have 8. This will also have 8, but there's 4 of them, so I'll multiply by 4. So that's 32 plus 8, that's 40, right? And and then the total number of valence electrons here is basically going to be 6, and then the fluorine here is 7 times 4, so that's 28 plus 6, that's 34. So the total number of bonds here should be 40 minus 34 divided by 2, which is 6 over 2, which is 3. There's 3 bonds in the structure. Now obviously there is going to be an issue here because of the fact that this kind of violates the octet rule, right? So that's one of the reasons behind why the number is, there only says that they have 3 bonds. So because this violates the octet rule, a potential arrangement of this, remember that the bonding atom tends to be a good host. So in that sense, the sulfur will donate 1 electron to each of these fluorines, right? And it'll have 2 more electrons for itself, right? So in this case, each fluorine I'm just going to do in green here, each fluorine will donate 1 and basically form a stable octet as shown. Okay, so this equation doesn't really work when you violate the octet rule. So the structural diagram of this, it should kind of look like this. Okay, and you can notice here from the structural diagram that we have 4 bonding atoms, 1 lone pair, and therefore 5 electron groups, right? And as a result, this basically indicates an electron geometry of trigonal bipyramidal. Now specifically, because we have 1 lone pair and we have 4 bonding atoms, they're going to create a different variant of the trigonal bipyramidal, which we stated would have 90 degrees and 120 degree bond angles. This is going to be called seesaw, right? So the molecular shape here is a seesaw, and the seesaw structure would kind of look like this, right? 1 bond goes out of the plane of the page, 1 goes into the plane of the page, and then there is a lone pair located out there, right? So in that sense, the lone pair was going to cause a slight deviation of less than 90 degrees here, and then we should still see the 120 degrees. Now let's draw out the structure here in the plane of the page. Okay, so in this case, you're going to have a sulfur here, a lone pair located here, a fluorine out here, a fluorine out here, and then one of the fluorine will go out of the plane of the page, and 1 will go into the plane of the page. Okay, so you should have fluorine there and a fluorine there. Okay, and that's basically what the structure will look like. Okay, so this is going to have a seesaw molecular geometry, and this is what sulfur tetrafluoride will look like. Okay, for the following compound, describe its electron geometry and molecular shape regarding VSEPR, right? Valence shell electron pair repulsion theory that will help us to determine 3-dimensional structures. Now this molecule here is called acetone, right? It's also known as propanone. I'm going to show you guys what this looks like. Now, first what we want to do here is I want to look at the total number of bonds you would expect to see in this structure. So I'm going to use this equation, total number of bonds is equal to total number of electrons in stable octet minus total number of valence electrons over 2, right? And in this case, you have carbon, you have hydrogen and you have oxygen, right? And carbon has 4 valence electrons, hydrogen has 1, and oxygen has 6. Okay, and you basically have 3 carbons, 6 hydrogens, 1 oxygen. Now I'm going to look at total number of electrons in stable octet for each of these. So carbon should have 8, because there's 3 of them. I'm going to do 8 times 3. Each hydrogen should have a max of 2 to create a stable octet, and because there's 6 hydrogen, we'll multiply by 6, and each oxygen should have 8, and there's 1 oxygen. So you have 8 plus 12, which is 20, 20 plus 24, which is 44. So there should be 44 electrons to make this molecule completely stable, in a sense that all the atoms have a stable octet. Now, the total number of valence electrons, so the electrons that are available, are there's 4 per carbon, because there's 3 carbon, we'll multiply by 3. There's 1 per hydrogen, there's 6 hydrogen, we'll multiply by 6. And there is 6 for the oxygen, and there's 1 of them, so I'll multiply by 1. So you get 12 plus 6, which is 18, plus 6, which is 24. So collectively, the total number of bonds you should see in your Lewis dot structure, in your structural diagram, and your VSEPR. Well, VSEPR not necessarily, because VSEPR double bonds and triple bonds will appear as single bonds, so it won't really matter. But for your Lewis dot and your structural, you should see 44 minus 24 divided by 2, which is basically 20 over 2. There should be 10 bonds. Okay, so to look at this, right, it's going to be a little overwhelming, because we should see multiple central atoms. So the potential central atoms that you can have are carbon, for the most part, or oxygen, right? So let's take a look at each of these guys. Okay, so these are potential central atoms. Potential layout that could satisfy these, if you have a carbon here, and a carbon here, right, and you made single bonds, and the carbons at the ends produced single bonds with the hydrogens, okay, that would constitute approximately 7 bonds, right? There's 3 here, 3 here, and then there will be 3 here, 3 here, that's 8 bonds, right? And then there's 1 here and 1 here, that's 8 bonds. And then the oxygen should be divalent, should only have a maximum of 2 bonds, so then this would be 10 bonds. Okay, so this is a potential structural. So I'm starting with the structural this time. I'm going to check this with my Lewis dot structure. So I'm just going to make the carbons in blue here, right? So basically each carbon, so here's a central carbon, and let's do another central carbon in green. And you can notice here that this actually will work out, right? That each hydrogen will donate 1 electron, and then receive 1 electron to form a stable octet. Same idea happens here, right? And this oxygen will donate 2 electrons, and it has a lone pair of 2. Now, so this is the idea, right? So you should see there should be 2 lone pairs there. And this is our Lewis dot structure. This is our structural diagram. And I'm going to look at my VSEPR. Now, I'm going to basically look at this guy as my central atom 1, central atom 2, and central atom 3. Okay? So looking at central atom 1, we can see that each carbon here, the central atom here, it doesn't have any lone pairs, right? It doesn't have any lone pairs, and has 3 bonding atoms, right? And in that sense, it should be tetrahedral. So the central atom 1 here has 4 bonding atoms, 0 lone pairs, and the steric number, or total number of electron groups, as 4, n is equal to 4. So the electron geometry here is tetrahedral. Okay, so this has tetrahedral electron geometry, and the structure of this is going to also be, the molecular shape is also going to be tetrahedral as well. Okay, we can imagine that the same idea happens for this guy. We'll call this central atom 3. Okay, for central atom 3, we'd have the same layout, right? So this would also be tetrahedral electron geometry and shape. Okay, so this would also be tetrahedral, right? Now, for this one, central atom 2, right, we have 3 bonding atoms no lone pairs. So for central atom 2, we actually have 3 electron groups, right? Or the sum of the bonding atoms plus lone pairs is 3. So this tells us, and this is because VSEPR doesn't account for double bonds and triple bonds, they're treated the same as a single bond. There's 3 bonding atoms and 0 lone pairs. This actually will look trigonal planar. Okay, so central atom 2, with respect to the 2 carbons and the double bond with the oxygen, will be trigonal planar, versus the other 2 carbons on the right, the very far left and far right side, are going to be tetrahedral. So this is a potential structure that I can create for this. Right, so carbon 1 will look like this. Okay, let's say there's a hydrogen in plane, carbon in plane, and then these 2 hydrogens are out of the plane. Okay, and then this bond angle could be 109.5 degrees, right? And then for carbon 2, this should be trigonal planar, right? So if this is trigonal planar, there should be a double bond here, right? And this bond angle here is 120 degrees. Okay, and then carbon 3, let's do this in blue. Carbon 3 would basically be tetrahedral as well, and it should look like that. And then this is bond 109.5 degrees. Okay, so that's really the idea, right? These are the lone pairs, right? So that's really the idea. So this would be the actual structure of acetone, and this is what acetone will look like in 3 dimensions. Okay, let's construct the VSEPR structure for this molecule. It's called methanol. And for looking at the VSEPR structure of methanol, let's first construct the Lewis dot structure. So the atoms we're going to be looking at in general, carbon, hydrogen, and oxygen, right? So this is an organic molecule. And in this case, we can notice that carbon has 4 valence electrons, right? So carbon has 4 valence electrons, hydrogen has 1, and oxygen has 6. Okay, so what I'm going to do is I'm going to do the analysis of the total number of bonds I would expect in this structure, total number of electrons in the stable octet minus total number of valence electrons divided by 2. Okay, so to do this, I'm going to start with carbon here. Okay, just that. Okay, so it's carbon, hydrogen, oxygen. Okay, we're going to have total number of electrons, stable octet, total number of valence electrons. So for the total number of electrons in the stable octet, we can notice here that there is 4 hydrogens, right? There's 3 here and 1 here, the way I just wrote it out. In this case, carbon should have 8, hydrogen should have 2, right, to create a stable octet. However, there's 4 hydrogen, and oxygen should have 8. So in total, we have 8 plus 8 plus 8, which is 24. Total number of valence electrons, carbon has 4, hydrogen has 1 times 4, and oxygen has 6. If I add these together, you get 14, okay? And then the total number of bonds here is basically 24 minus 14 over 2, which is 10 over 2, which is 5. So there should be 5 bonds in this structure. However, we know that the central atom, just by looking at this, we know hydrogen is never the central atom, and carbon is the least electronegative, so carbon is a central atom. However, carbon is only tetravalent. There's 5 bonds here, so this indicates that there's going to be 2 central atoms. So the second central atom here is oxygen, because hydrogen is too small to be a central atom. So potential layout of this can potentially look like this, right? So the carbons can be bonded with hydrogens, there could be an oxygen here and a hydrogen here. And to test this, I'm going to do the Lewis dot structure. So I'm going to do carbon's electrons in red. So carbon donates 1 electron to each hydrogen, okay? And it receives 1 electron back. So let's do hydrogens in green here. Okay, it receives 1 electron back. Okay, so it kind of helps when you use different colors to see this, right? And the oxygen will donate, let's do oxygen's electrons in orange. The oxygen donates 1 electron here and 1 electron there, and it has these 2 lone pairs, right? So this hydrogen here should also donate 1 electron. Okay, you can see that now we actually have stable octet for all the species, right? So this was the Lewis dot structure, right? So this is the Lewis dot structure, but let's convert this to structural, where we're not just looking at bonding electrons as these dots, we're going to use them as lines, right? So this is a bonding electron, bonding electron, bonding electron, bonding electron, bonding electron, and then these guys here are our lone pairs. So this and this is a lone pair, right? So collectively, our structure here would look like this. So this is my structural diagram. So you can notice that these are all single bonds, and then we have two lone pairs here. And if we're looking at, we'll call this like the central atom 1, so we'll call it C1, and we'll call this the central atom 2, C2. If we're looking at the central atom 1, right, if we're looking at the electron geometry of central atom 1, this guy has 0 lone pairs and 4 bonding atoms. And the way I'm looking at this is I'm looking at the steric number, or the total number of electron groups, bonding atoms, and lone pairs, right? So the bonding atoms plus lone pairs gives us the total number of electron groups. In this case, we have 4. The electron geometry will match the molecular shape, and both of these cases would be tetrahedral. Okay, so the carbon, the central atom 1 here, should be tetrahedral, right? Let's take a look at the oxygen. If we take a look at this oxygen, this guy has 2 lone pairs, 2 bonding atoms, the carbon and the hydrogen, and it still has a steric number 4. This indicates we have tetrahedral electron geometry, but the molecular shape is going to be different. The molecular shape here is angular bent, V-shaped. Okay, so the oxygen with respect to the carbon and hydrogen should be bent, right? So there's actually 2 central atoms, and that's why it makes it a little bit more difficult, right? So one of our central atoms here was the carbon, and the other central atom, here was the oxygen. So I'm gonna draw this based on these findings. So the carbon relative to the 3 hydrogens and the oxygen should be tetrahedral. So let's say carbon, it looks like this, okay? So there's a hydrogen here. There is 1 hydrogen that's going out of the page, right? 1 that's going into the page, and then maybe this is connected to this oxygen, okay? And you don't have to put the oxygen in the plane of the page. You can keep it out of the page, it doesn't matter, right? And then this oxygen has basically 1 lone pair here and 1 lone pair here. Remember, the lone pairs tend to be, they're also kind of like considered bonds, right? So let's just kind of make this a little bit more visible, maybe. Let's use a different color. There's a lone pair here, a lone pair here, right? And then this oxygen is going to be connected to this hydrogen, and this is going to be angular bent V-shaped, right? So this bond angle should be less than 109.5 degrees. It's approximately 104.5 degrees, but this bond angle is tetrahedral and should be 109.5 degrees, right? So this is what the structure would look like, right? So we're going to actually have 2 different bond angles because we have 2 different central atoms. Now if I look at this in terms of a plane, right, if this is my plane here, okay, so this is my plane, what you can draw out here is, I'm going to say the carbon here is like that, there's a hydrogen here, you know, there's an oxygen here, it has 2 lone pairs, right, and this is going to be in the same plane, right, but we can understand that one of the bonds is going out this way, so let's say that it's going out this way, right, so it's kind of like above the plane of the page, okay, and the other bond is going into the plane of the page, so it's below this plane, right, and the bond length should be the same length. I'm drawing a sketch here, so it's not drawn exactly or proportionally, but you guys can imagine that this is the plane of the page, one is below, one is above, right, and then these are going to be in the plane of the page, right, so that's the idea. So it does get a little bit more complicated when you have multiple central atoms.